In these problems, we're being asked to find the inverses of matrices when they exist. So what does that mean, the inverse of a matrix? Well, you know, the inverse of a number we usually think of as something where if you multiply it by itself by that, it would equal 1. So if I had the number 4 and I multiplied it by 1/4, that would equal 1. So in some way, 1/4 is the inverse of 4. With a matrix, it's a little more tricky. We have something called the identity matrix. For a 2 by 2, the identity matrix looks like this. For a 3 by 3, it looks like this. So the ones kind of make a diagonal down the center there. And the definition of an inverse of a matrix is that if you multiply a matrix by its inverse, you get the identity matrix. You get this guy. When we're dealing with 2 by 2 matrices, it's pretty easy. There's a pretty easy formula to plug and crunch it out. With a 3 by 3, that formula is much more complicated, and there's an alternate method you can do that I'm going to show you here now. You make what some people call an augmented matrix by slapping this identity matrix on the other side of it, and then doing some manipulation until you turn the first part of the matrix, this thing here, into the identity matrix. Let me show you how that works. I'm going to rewrite this matrix here. I have 1, 0, 1, 1, 1, negative 2, 0, 1, negative 2, and now I'm going to just do a little dashed line here. I'm going to put in this identity matrix. So 1, 0, 0, 0, 1, 0, and 0, 0, 1. Now what I'm going to do, I'm going to try, this is kind of a process of trial and error, I'm going to try to apply what are called row operations. So I'm allowed to manipulate these rows. I could take row 2 and add it to row 1. If I did that here, I would need to just do it here. This side kind of keeps track of all the manipulations I'm performing on this thing. I could multiply a whole row by a constant if I wanted to. I could take one row, add it to the other row, but that row multiplied by a constant and then add it to that row. I could also switch rows around if I wanted to. As long as I do what I do over here, I do over here. So I'm going to see what we can do here. And bear in mind, I'm trying to turn this side into this side. I want it to look just like that. So let me see. I think I'm just going to start here. There's no one right way to do this. You just kind of cast around until you find a method that works. I'm going to take to row 2, I'm going to add 2 times row 1. I want to do that because I want this number to go to 0 because I've got a 0 over here. So I'm going to do that. What I get when I do that, so row 1 stays the same. Row 2 gets multiplied by 2 times row 1. So 2 times 1 is 2, or sorry, added to that. So 2 times 1 is 2 plus the 1 is going to be a 3 now here. 0, well, 0 times 2 is nothing, so the 1 stays the same. And then 1 times 2 is 2 plus a negative 2 is 0. And then we didn't do anything to the third row. So that stays the same. So that's my changes so far. I've got to apply the same thing over here. So row 1 stays the same, row 3 stays the same. But row 2, I add twice row 1 to it. So that would just be a 2 here. The 1 would stay the same, the 0 would stay the same. Okay, so I'm a little bit closer. Let's see what can I do next to this. I think I'm going to add, oops, this is a negative 2. That makes a difference. I think I'm going to add 3 times row 1, so to row 3. So we're going to plus 3 row 1 here. I'm going to run out of room here, I have a feeling, but let's try this. So 3 times row 1. Row 1 is going to stay the same, so I've got 1, 0, 1. And row 3 is going to stay the same, and I've got 3, 1, 0. And row 3, I'm multiplying this by 3 and adding it to it, so I'm going to get 3. That 1 will stay the same. And the negative 2, add 3 to it, will be 1. Okay. Now let's make sure I do the same to my augmented side here. So I've got 1, 0, 0, 2, 1, 0, and this will become 3, 0, and the 1 stays. Okay. I think we're getting closer. Might not look like it, but I think we are. I've got my 1s on the diagonal. I've just got to kind of get rid of all these other things now, make them all go to 0. So let's see what we can do. I'm going to take row 3 and subtract row 2 from it. That will be some nice progress. So row 1 stays the same, row 2 stays the same, and row 3 is going to become 0, 0, 1, and that's exactly what we want in row 3 because we're trying to make it look like that identity matrix, so it's already there. All right, now let's see what we have to do to the other side. Row 1 stays the same, row 2 stays the same, row 3, we're going to subtract row 2 from it, so this would be 1, negative 1, 1. At this point, I think I can make row 1 good by subtracting row 3 from it, because all I want to do is get rid of this guy. So row 1 minus row 3 will make that look like 1, 0, 0, 3, 1, 0, and 0, 0, 1. I am almost there. And let's see, I subtracted row 3, so I would get a 0 there. Subtracting a negative 1 is like adding it, and then a negative 1 there. The other rows stay the same. I think the last thing I would need to do is subtract 3 times row 1 from row 2, and that should do it. So this is row 2 minus 3 times row 1. So row 1 is going to stay the same, 1, 0, 0. Row 3, we're going to subtract 3 times this, so that only affects the first number because these two are 0 up here. So I get 0, 1, 0. And here, that stays the same. So I have achieved my identity matrix here on the left side, but let's make sure we figure out what happens to the right side. So row 1 stays the same, 0, 1, negative 1. And this is going to become, so I'm subtracting 3 times row 1. So the 2 stays the same. I subtract a 3 from a 1, that's a negative 2. I subtract a negative 3, so that becomes a positive 3. And the last row stays the same, so 1, negative 1, 1. And there we have it. I've converted this side to the identity matrix, so this right here is the inverse of the matrix that we started with. This is the inverse of this. And if you're skeptical and you want to test, all you have to do is multiply this times this, and you should get the identity matrix. Let me show you a slightly easier way to do this with 2 by 2 matrices. So it says find the matrix if it exists, and the formula for the matrix, the inverse of a 2 by 2 matrix looks like this. This is the inverse of matrix A, is going to equal 1 over the determinant of A, so I'll just write that like this, times, and if the original was A, B, C, D, like this, then in the inverse it's going to be D, negative B, negative C, A, like that. So really, all you need to do is find the determinant and then do a little bit of switching around of numbers. So let's give this a try. So 3 times 8 is 24, minus 6 times 4 is 24, and that equals 0, and uh-oh, at this point we need to stop because we have a division by 0 problem. And what this means is that if the determinant of your matrix is 0, an inverse does not exist. So you can just stop right there and say that it does not exist. Let's try this next one. So let's figure out our determinant. 3 times a negative 2, that's negative 6, minus 20. So that's a negative 26. So this matrix is definitely going to have an inverse. We'll take a look at our formula again. I've figured out the determinant, so our inverse is 1 over the determinant times, and the D goes up here, and that's negative 2. A negative B goes up here, so that's negative 5. A negative C right there, so that's negative 4. And A right here, A is 3. And now what I'll do is I'll multiply our constant through here. So the inverse equals negative 2 over negative 26. That's going to be a positive 1/13. Negative 5 over negative 26. That's going to be 5/26. Negative 4 over negative 26. That's going to be a positive 2/13. And 3 over negative 26, that's going to be a negative 3/26. And that is our inverse. So that's a little bit of work with finding the inverse of inverses of matrices.